All right, good morning, guys. It's Wednesday morning, so if you haven't heard yet, did have my baby yesterday at about 4 o'clock. His name is Bryden Ray Patrick Smith, and he's doing very well. Him and mommy are doing well. So I just ran home to try and shoot some videos and get ready for today's class. So I definitely appreciate it if you guys did your best. We will try to catch up together on Friday when I return. But if you guys could put forth your best effort to try what we're doing today, that would make things easier on me for sure. Excuse me. My printer at home is almost out of ink, but you guys have this document in front of you, so we should be fine there. Hopefully you are pretty good now at using the slope formula to calculate slope. We're going to talk about slope in terms as a rate of change today. So how do we define a rate? A rate is a comparison of two quantities with different units. And we're going to look at just a couple examples right here. So our first one, Simon traveled 120 kilometers in 2 hours. This is an example of a rate that you see all the time when you're on the road, whether you're on your bike and you have a speedometer, whether you're just in the car with your family and you look at the speedometer. You can get a speed from this. So the rate here is 120 kilometers per 2 hours. So that would be like expressing it as a rate, 100 kilometers per 2 hours. Or we can write that more simply as our speed, 60 kilometers per hour. And most often we do express that as a unit rate, the number of kilometers for 1 hour. You know what, you guys can, if you want, quickly pause the video and try to find the unit rate for number 2. 12 pencils for 240. Okay, so it's actually a couple ways we could find a unit rate here. We could find how many dollars is it per pencil, or we could find how many pencils could you get for $1. A couple different unit rates. So let's actually just do both. So 12 pencils per $2.40. You can do 12 divided by 2.4, and you get exactly 5. And this quantity tells you, because we did pencils divided by dollars, pencils per dollar. 5 pencils for $1. It's a unit rate. Alternatively, if you did 240 divided by 12 pencils, this gives you something different. You get 0.2, and this time we did dollars divided by pencils. 0.2 or 20 cents per pencil. So we use rates and unit rates all the time in our everyday lives. So you guys have on your handout, it's a bit easier to see. We're right here now. Slope is considered to be a rate of change. Which simply means that a rate of change, so rate of change, ROC, is the change in one quantity relative to the change in another. So slope is kind of like a rate of change because slope is like the change in the rise over the change in the run. So we're going to go through an example here. Now, at least my graph shows up here. I actually have to flip back to my note just so I can read that question. For Tom and Sarah runs 5 kilometers in 20 minutes. So that's like a rate. And Tom, 7 kilometers in 30 minutes. And then we're going to find the rate of change for both students, and we're going to graph each one for Sarah and Tom. And then for part C, we're going to find what the rate of change means in this scenario. I'm just writing this down. It's been a very busy time. No time to get printer ink. Who is running faster? So right now it's a little hard to tell just by looking at it. Maybe some of you guys can mentally. How? And then 3, how is this shown on the graph? Perfect. All right. Back to our note here. So let's do the rate of change for Sarah first. Now here, the unit rates, when we usually work with distance and time, we're usually looking for some kind of speed. So for Sarah, we have the rate of change. She runs 5 kilometers per 20 minutes. As a unit rate, 5 divided by 20, 0.25 kilometers per minute. And for Tom, the rate of change, 7 kilometers per 30 minutes. And right now it's not apparent who is faster, but when we find the unit rate and do 7 divided by 30, I'll carry a couple decimal places here, 0.23 kilometers per minute. So if we had to sort out who was the faster runner, well, that would be Sarah. She travels more kilometers per minute. So let's get this on a graph. Now usually with distance and time problems, we put time on the horizontal axis, and our time will be in minutes. And just squeeze this in here. Distance in kilometers. Now I'm going to go up by tens here. So every 1 block horizontally is 10 minutes. And then let's see what we can fit on here. Yeah, let's do every 1 box vertically, we'll say is going to represent 2 kilometers. So I can fit a few different points on here. So I'm going to do Sarah in blue here. So let's say Sarah, initially before she starts running, she's ran no kilometers, and then the clock starts. She runs 5 kilometers every 20 minutes. So in 20 minutes, 5 kilometers. That's like, and I'll add it for this one, not for others though. It's like the ordered pair, 20, 5. And then in another 20 minutes, she's run another 5 kilometers. In another 20, another 5, up to 15. And I'm just going to go as far as I can on my graph here, which is right about there. And there we've kind of graphed Sarah's progress over time. And now let's map Tom's. So Tom runs every 30 minutes, 7 kilometers. So 37. That ordered pair right there. Another 30, another 7, up to 14. 37, 37. And we can see that we graph those out. Those two lines are very close together, but you can definitely see that Sarah, my blue line, is definitely making more progress than, or moving faster than Tom. We're going to talk about how we can determine that just by looking at the graph. Now, if you guys have a straight edge, you might want to connect those. At home here, I have my limited resources, so I'm just going to leave it. So as you've probably seen here, when we found that rate of change, the rate of change in this scenario gave us a speed. Who is faster in this scenario? Well, by finding that rate of change, we saw that Sarah travels faster than Tom. And here's the big thing. How is this shown on the graph? Shown on the graph, the slope of Sarah's line, i.e. her rate of change, is highest. The steeper the line, the faster the rate of change. And in this case, because rate of change is measuring speed, the steeper the line, the higher the speed. So if you need to pause and get something down or clarify something with your covering teacher, then do that. We're going to go on to page number 2, second example. This is before my printer ran out of ink. So here's a very just rough graph showing the volume in a gasoline tank remaining after the car is driven a certain amount of kilometers. So in part A, let's do the slope of this graph. So actually, you guys can pause the video, take a moment or two, apply the slope formula. Ideally, at this point, you're pretty comfortable using it. And then we can unpause and then move forward. Okay, so I'm going to calculate my slope here, y2 minus y1 over x2 minus x1. We already know by looking at the graph our slope should be negative. So if you do your slope and it's positive, you should have a little alarm bells going off and just maybe see if you can find your mistake. But here we have 5 minus 65 all over 500 minus 0, which gives us minus 60 over 500. Now, in lowest terms, I can divide each of those by 20 and get minus 3 over 25. And I could leave it just like that, and that's just fine. Or, and this may be practical for some applications, we could get that as a decimal. 3 over 25, I believe that is negative 0.12. So we found the slope, minus 3 over 25, or minus 0.12. What is the rate of change? Well, we divided using our slope. We divided the rise by the run. Well, the rise corresponds to the change in y values, which is our volume. It's a change in volume. Over the run, a change in distance. So we did here, we divided volume by distance. So I'm going to write this two ways. First, with our minus 3 over 25, that means it's negative 3 liters per 25 kilometers. The volume in the tank goes down by 3 liters. You burn 3 liters of gas for every 25 kilometers you drive. As a unit rate, that decimal, negative by dividing, negative 0.12 liters per kilometer. Every kilometer you drive, you use up 1 liter or 0.12 liters of gas. Notice negative. You don't magically gain 0.12 liters of gas every kilometer you drive. If you could find a way to make that happen, you'd be a millionaire for sure. No, we lose liters of gas for how far we drive. So in this scenario, for every kilometer we drive, we burn 0.12 liters of fuel. If you had said for every 25 kilometers you drive, you burn 3 liters of fuel, that means the exact same thing. They're equivalent. All right. One more example. Here, we don't have a graph per se. We have a table of values. We can still find the rate of change fairly easily. If you go up, and we'll look at more of this later, but if you look at how much in this first one, time versus total pay, how much it's going up by, each entry in this table, the right-hand column anyway, is going up by 25. The total pay column is going up by 25. Be careful, that doesn't mean that this person is getting paid $25 per hour, because these time intervals are going up by 2. And I might emphasize, actually it's okay, let's leave it as 2. They're going up by 2, positive 2. So if we think of this just like these as ordered pairs, x and y, we can find the rate of change much like we do slope. Think of it as rise over run, the change in y over change in x. We have the change in y is $25 per every 2 hours. And here the rate of change, when you divide 25 by 2, gives you 12.5, or in this case, $12.50, and we divided dollars per hour. So this table, that rate of change, represents this person's wage, their salary per hour. Can you guys take a moment, pause the video, try this for the second table, and then we'll wrap things up, connecting slope and rate of change. All right, so for the last example, the cost column is going up by 500 each time. The number of people is going up by 20 each time. So for every increase of 20 people, the cost goes up by 500. So the rate of change here, change in y over change in x, that's 500, and that would be dollars per 20 people. And then doing that division, 500 divided by 20, we get 25. That would be dollars per person. So here that unit rate gives you the cost per person at this banquet. So finally, How are slope and rate of change connected? Well, they are connected very intimately. When a relation is graphed, like we did earlier, and like we saw in our second question, the slope describes the rate of change. So slope describes rate of change. Now I made that little caveat when a relation is graphed because rate of change, let's add this below in red. When you calculate a rate of change, it's a rate. It has units. It's a comparison of two quantities. It has units. When you graph and find a slope does not have units. But when we graph a relation, the slope describes the rate of change. Numerically, they are similar, but the rate of change will have units. When we graph it and find slope, no units. But they are tied together, rate of change and slope. So I hope that lesson went okay for you guys. Again, if you need to pause, back up, ask a question, please make sure you do so. I'm going to leave some text practice questions with your covering teacher. Hopefully things go well. I will be seeing you guys on Friday. I'll be in for parent teachers if your parents want to talk to me or you want to come visit as well. But I will not be in Thursday. I'm going to be taking my last day I have off with the new baby. And just as a little treat before you guys go, see if the camera picks this up. There is little bridey boy. That was last night, doing very well. Okay, so looking forward to seeing you guys. Work hard, and we'll see you soon. Bye-bye.